Don't do it, creature. Creature says good morning. Alrighty, so today we are going to start our chapter on chemical reactions. Let me just put him up on the couch. Hush, little dude. Okay. Good morning, Brittany. Okay, so we're going to talk about chemical reactions today. So we've spent kind of 75% of the semester or so talking about various properties of matter. Yes, he does want to hang out. Creature, hush. Hush. Let me go put him in the bedroom instead, maybe. Yeah, he's very mad this morning. Relax, dude. You're fine. You don't need to go steal other people's food. Okay, maybe he's calmed down. Always an exciting time, right? Alright, that's enough. Come on. 1 second, guys. Right, that's always an exciting start to the morning, right? Okay, so he can bark all he wants in the bedroom. Hopefully that's not going to disturb us. So chemical reactions. We've talked about various properties of matter. We've talked about states of matter. We've talked about chemical formulas. We did a couple of things with those. We did empirical formulas and that sort of thing. We did naming. We really just focused on maybe one or two things at a time. Going on, right? So we would look at, one set of gas molecules or, one thing that's in the solid phase. Yeah, right, exactly. It's just... and it's only during class time, right? Go figure. But now we're actually going to start kind of branching out into things that carry multiple components. So these reactions we're going to see will involve multiple components going on, undergoing a chemical change, in order to become something new. So, a chemical reaction kind of looks like this. You'll have your reactant or reactants turning into your product or your products. Whichever, you can have multiple of either one. You could have two reactants becoming one product, two reactants becoming three products, one reactant becoming three products. I mean, there's also there's no limit in that regard. So you can have whatever your reactants are turning into products. Sometimes you'll see reagent instead of reactant. They essentially mean the same thing for us. So reagent, I guess, is typically more used in organic chemistry for some reason. It's not really, there's no real difference for us. So you might see that as well. Okay, but suffice it to say, it's something as a reactant, and that'll turn into your products over the course of a reaction. So let's go ahead. Let's see. So these are, of course, chemical changes, right? So we're finally getting into actual composition change. So in this chapter, we're going to learn how to predict the products of many different types of chemical reactions that are happening, as well as go into quite a bit of detail about what's actually happening there chemistry-wise. So let me give you an example of a reaction just so we can identify some things about this. Actually, let's make this sulfuric acid instead. Oh my gosh, I don't know how to write. We're going to learn how to be able to predict all of these things in a chemical reaction. So let's just, this is an example of one. Let's go ahead and kind of break it apart here. So we have our reactants. That's going to be sulfuric acid. Oh dear, the creature has escaped. And sodium hydroxide. And our products are going to be sodium sulfate and water. Let's see if I can't get this to work. Creature, come here. You're just gonna sit on Daddy's lap, okay? Okay, so with those, we can also look at some other things that are interesting in this reaction. We have, for example, these little parentheses things after all of our compounds. And so those are all states of matter. And you're going to learn how to predict the state of matter for a particular component in a reaction as well. So just so we remember, we'll talk about this in a second, what the different states are that we'll see in reactions. And then we have a few more things. If we notice here, these are reaction coefficients. And so essentially, while we're not writing it here, we would have one of that and one of that. We just typically leave it blank if it's just a 1. And so your reaction coefficients are going to be how many of that substance, whether it's a molecule or an atom or an ionic compound, are required. So think of your reaction coefficients as if you were reading a recipe and it's saying, okay, you need to put in 2 eggs. That would be analogous to this 2 NaOH that we have here. So your reaction coefficients are just kind of your quantity of how many you need for a reaction to take place. So this reaction coefficients right now are telling us we need 1 molecule of sulfuric acid plus 2 units of sodium hydroxide for this reaction to go. And once we have done so, we're going to get 1 unit of sodium sulfate out and 2 units of water. And so that's what those coefficients mean. We're going to see as well how to work with those in a little bit later. Okay? So that's kind of what a chemical reaction looks like. So any questions on that before we start learning some different types? Oh, I guess I should tell us what the states of matter are, huh? So we're going to have 4 states of matter that we have. We, of course, have solid, which I can't spell. We have liquid. We have gas. And then we have the 4th one, which is going to be aqueous. And so we abbreviate those like this. And we're going to see that this is important for being able to predict physically what's happening in a reaction. So some of our evidence that reactions are happening would be formations of a certain one of these states of matter. For example, if we're mixing 2 aqueous things like we had in this reaction, we're now producing a liquid. Well, that may not be super obvious to us. When we're producing a liquid, we're going to learn we also produce a lot of heat. Ones that are more obvious would be, yeah, right? The letters finally actually match the words. It's a miracle. So that's always good. right? So we're going to see, and in the textbook, I have a bunch of examples of different types of reactions for you guys that we can look at. We can look at those on Monday, just for those of you who don't have the textbook, so we can all see some of the cool stuff that's happening. So with that, we can go ahead and, now that we kind of have the toolkit necessary. Oh, good. Yeah. The chemical reactions are my favorites. I liked recording those. So, yeah, we'll watch those on a Monday, I think. Yes, Creature, you can watch them too. Okay. So, we're going to see that we're going to have types of reactions. And so we're going to have 5 major types that we're going to talk about in this course, which we're going to start with basically how the components are interacting together. And then we'll kind of switch gears and talk about reaction types based on evidence. So we're going to see reactions that produce solid products, reactions that produce gas products, reactions that produce liquids, or reactions that involve electron transfer. So, but for right now, we're going to talk about chemistry speaking. And so our easiest type of reaction, actually there's kind of 2 of them, is called a combination reaction. And these are going to be ones where we have 2 things reacting together to make a third thing. For example, if we were to react sodium metal with chlorine gas, we would get sodium chloride out. This is a combination reaction. We're combining sodium and chlorine together. The sodium is going to end up kicking or losing its electron, giving it to chlorine, and they're going to form the ionic compound sodium chloride there. Oz, what are you doing now? Are you trying to get in there? Okay, here, go ahead. Yes, this is also known as synthesis. That is a good point. Those are the same name. So these reactions are the same name. You're just putting 2 things together and making a third one. For us, that would we would only be, if we were to try and guess the products of a synthesis reaction, for us this is going to be only for ionic compounds. So I'm not going to, we're going to learn in Gen Chem 1, if you have to take that, how to predict the products of more complicated synthesis reactions. But for right now, it'll just be ionic ones. So, for example, we know that sodium prefers a charge of +1, chlorine prefers a charge of -1. We know that we know how to charge balance an ionic compound. So, for example, if we were to take potassium and oxygen gas, what is the product going to be of that? Creature, you're just... Now he's like dying in my arms. Sweetie, naughty creature. So what do we think the product is going to be if we combine potassium and oxygen together? Is there a particular charge that potassium likes? Yeah, absolutely. Yeah, absolutely. Very nice. I'm glad you remember your charge balancing. That's good. So note that that is K plus O2 minus, right? We know that these are the preferred charges of these elements, so putting them together we should get K2O. And lo and behold, there we go. That is the product of our combination reaction. All right, how about another one? Let's see, what would be a good ionic compound? Creature, what's your favorite ionic compound? Oh, really? All right, let's put aluminum and sulfur together. So you want to remember what the charges are for those ones, and that's all we'll need to do. Oz, what are you whining about, mister? Yeah, so for this, you'll probably want to have a periodic table nearby, just for ease of access. Yeah, exactly. So we're going to get Al2S3, right? Because we know that aluminum is 3 plus, sulfur likes 2 minus. Perfect, perfect. So note right now, we're not talking about balancing the equations, so we're going to see the subscripts can be different on both sides of the reaction, no problem. We'll address that in a little bit. So for right now, we're just putting things together. I believe this is actually what Kenji had mentioned as like a skeleton reaction. It's kind of just the very bare bones, as it were. So we're just taking our, compounds, putting them together, and we're getting our product. We're not worried about states of matter. We're not worrying about balancing. We're not worried about any of that stuff right now. So that's, I guess, stuff we're going to add on as we flesh out all of this stuff. Sorry for all the puns. I usually don't make puns like that. Okay, so combination reaction, easy, yeah? Just remember what the charge is. Yeah, well, we'll talk about that later on. So first I'm going to introduce all the different types. We're going to go into balancing afterwards. And we'll talk about states of matter afterwards as well. Alrighty, so then let's move on to our second one, which is called decomposition, and that is the exact opposite. Wow. Where we'll have something breaking apart. And so we're going to see that these will be a bit harder to identify. Well, no, you can identify these pretty easy, but figure out the products can be tricky with these. But let's just do one example that maybe we have heard before. This would be an example of a decomposition reaction. We're taking hydrogen peroxide and it's breaking down into water and oxygen. By the way, anytime I say oxygen in terms of a chemical reaction, it's always O2, just like it was in gases and all that stuff. So this is probably not something I would expect you guys to be able to come up with the products for this particular one, but we will learn a couple of them that I would expect you to learn. Okay, but we see here, again, we have one thing breaking down into two things. So that is going to be our decomposition. Alrighty, so one that I would expect you to know is something of a carbonate. When you heat a carbonate, that little delta there, that means heat. When you heat a carbonate of something, you're going to get the oxide plus carbon dioxide gas. This is a pattern. Most carbonates will do this. So you have some sort of carbonate here. You produce the corresponding oxide plus carbon dioxide. And so this is going to be a pattern that we're going to see. So carbonates, when you heat them, you can get them to break down into oxides as well as carbon dioxide. So if you have, I guess I shouldn't recommend you do this at home, but if you have real chalk, that is to say calcium carbonate, not calcium sulfate, but like chalk, you can try heating it up. You'll see potentially. No, not necessarily. Oftentimes I actually will omit it. Some reactions you'll just need heat to get them to work anyway. For example, the combination reaction, you have to heat this up to get it to form MgO. You'll learn all about how to deal with this particular heat problem in Gen Chem 2. Thermodynamics is a very tricky business. Not something we need to go into. So, quick answer for you: no, that does not immediately mean decomposition. However, if you only have one reactant, that's what's going to tell you it's decomposition. So, whether or not the heat is there. I'm going to just erase this so we don't get confused there. So, in that case, what do you think would happen if we were to heat up sodium carbonate? What do we think is going to happen here? Yeah, exactly. We're going to get sodium oxide, Na2O, plus carbon dioxide. Hooray! Almost, Brittany. So don't forget, while calcium takes a +2 charge, sodium is only 1 plus. So you're going to need the 2 on the bottom there to balance out the oxide. Yep, awesome. Alrighty, so same thing here. We had some sort of carbonate. We have formed some oxide and CO2. Notice here it was calcium carbonate, and therefore we formed calcium oxide. Here we did sodium carbonate, and we formed sodium oxide. So yeah, the charge, you're always going to have charge balancing happen for your, you could do crisscross. So you would get Na2O doing the crisscross, for sure. So, yeah, that's definitely still something you can do. But for this particular reaction, honestly, you just have to take CO2 out of the formula here. And whatever you're left with will be your oxide. So notice if we just subtract CO2 from this calcium carbonate, I mean, I don't want to introduce it like an equation, but if we do that, we'll end up with that. So for this particular one, this sort of algebra works. So same thing. So we're not removing any sodiums from this, so we're good. Alrighty. Certain oxides will also decompose if you heat them up. For example, if you heat up mercury 2 oxide or silver oxide, you will get the metal out plus oxygen. So if you heat up an oxide, you just basically break it up into its elements, and that's it. Pretty boring one. And honestly, that's only for a few things. Like a lot of oxides will not do this, but a couple of them will. So I'm only going to give you ones that would do this, right? So if I were to tell you, okay, what if we had, I don't know, I'm just assuming let's just pretend tin oxide would do this. If we are going to break tin oxide apart, what do we think we're going to get? Tin 2 oxide, I guess, in this case. What do we think we're going to get here? None of these are ever trick questions, by the way, so don't be worried about that sort of thing. Any ideas? Yeah, that's it. Easy. Just break it apart. All we gotta do. So remember, oxygen always is O2 when it's just by itself. That's just how it always occurs. And so you would just break this apart to form the metal by itself and oxygen. That's it. So there's our decomposition reactions. So just to clarify here, I will either ask you to predict the products of a reaction or to simply identify the type of reaction. So for synthesis reactions, going back up, I can ask you to predict the products of something like this, where it's an ionic compound that's going to be formed. So those you should be able to come up with the products. You should also be able to understand that if we're just putting two things together and making a third thing, that we're going to get, that it's going to be a combination reaction. Without having to know what the products are. Well, for that one, you'd be given the products anyway. So you have to be able to identify and then predict the products for the cases I'm telling you. So for decomposition, you would be expected to produce the product of a carbonate decomposing as well as an oxide decomposing. And so that's just the two cases we've done here. That's the entirety of our decomposition product predicting. So that's all we have there. Okay. Alrighty, let's move on to type number 3 then, which is a combustion reaction. This is typically some sort of hydrocarbon. So while we don't necessarily have an A plus B equals C type of thing here, 3 of your components will always be the same for a combustion reaction. So for example, if we take propane, we would combine it with oxygen and we would make carbon dioxide and water. If we were to take butane, guess what we would make? We would make the same things. If we take some crazy compound plus oxygen, what do we think we're going to get out of this one? Are we going to get the creature? Naughty. Naughty creature. What are the products going to be? Hooray! Yes, Sherry's got it. Your products are always carbon dioxide and water. We could also have oxygen as part of our hydrocarbon. Guess what we would get? Hey, look. It's glycolysis. Or rather, that's glucose metabolism, I guess, all over the place. But you could also just burn glucose, and you would get the same thing as if your body were doing it, or some organism was doing it. So you can have oxygen as part of your hydrocarbon as well. So hopefully that reaction is the easiest one of all to predict, because the products are always the same. So, easy. Alrighty, so we have done our easy ones. We're going to go on to the more difficult ones now. Or they're not necessarily more difficult, they just require a bit more thinking. Or maybe not. I mean, it's up to you how you like to think about things. Alrighty. So a double displacement reaction will be our next type. It's also known as metathesis. But no one ever calls it that. Yeah, right? What's the product of this? H2O and CO2. Yeah. Yeah, so metathesis would be a name that you might see, but again, it's not a common one. This is used by people who want to sound stupidly smart for some reason. So, and how these works is you're going to have two ionic compounds producing two different ionic compounds. If we want to think about this in terms of fun colors, purple, yes. What we'll get as I switch through all of our colors here, purple is next. Okay, there we go. What we're doing here is we're swapping partners. So, you know, I guess it's kind of common for people to talk about this in terms of like a school dance or something. Or rather, a dance from like the 1800s or whatever, where people like actually danced and swapped partners and stuff in those crazy circular things. I mean, you've all seen the British period dramas, right? Where they're all dancing around and switching and stuff. This is what's happening here. We're swapping partners. So the negative part that was with Y, or so the negative part that was with B is now going to be with A. The negative part that was with A is now going to be with B. So they're just swapping. So we're going to basically be making, let's use light blue. We're mixing these two guys together and these two guys together. We're just swapping them. And as you can see here, I've done this with colors as well. So dark blue was with the red one, and now dark blue is with the green one. Purple was with the green one, now it's with the red one. So they've just swapped. So let's see what this kind of looks like. Yeah, right? That would be very nice for us, wouldn't it? Alrighty, so looking at this, we're going to want to look at our cation from one of them and the anion from the other one. And we're going to put those together. And so that became our calcium sulfate. So notice that was, we have to remember our charges, of course. So calcium is 2 plus, sulfate is 2 minus. So those are already charge balanced. And we're going to want to do the same thing here. And that one's going to give us our other product. 1 second, please. Okay. Let's have a look. Aha. So let's look at that. So in calcium chloride, yeah, I turned the mic back on. Okay. So remember, this means we have 1 calcium ion, 2 chloride ions. That's what that means. So if these are our ions we're putting together, crisscross it if you like, they're both 1. So you should get this. If you were to have, so Cl2 is not an anion, it's just Cl minus, right? That 2 there is telling you how many of that ion are needed to balance the calcium. So you're going to form NaCl, not NaCl2, right? I mean, there would be a lot of things that would make me very sad. All of these would make me very sad if someone were to write them. So remember, the reason we're able to name ionic compounds so simply is because they will only ever form 1 compound with each other. If you put sodium chloride together, sodium and chloride together, you're going to get NaCl. That's it. You're not going to get any other possibility for a compound there between sodium and chlorine. So it's very important when you're predicting the products of this that you look at individual ions and you put them together. So with this, we saw that we had Na plus from the sodium sulfate, we had Cl minus from the calcium chloride, and that's what's going to become our sodium chloride at the end. I think let's do plenty of practice with this type. Let's see, what would be a good one? Let's see if we can't figure out what the products of this reaction are going to be. And I'll show you another trick in a bit. What did I say was green last time? The Y, okay. Purple was... Sorry to keep doing this, potassium. Nitrate would be the red one then. So if you're looking at these, if you're trying to predict the products, what may be beneficial would be to separate the ionic compounds into their ions. So for example, silver nitrate is made of the silver ion and the nitrate ion. Potassium carbonate is made of the potassium ion and the carbonate ion. So if we're swapping these, yeah, oh, so close, Lamonda. One thing is missing from your answer. But yes, notice we're going to be making a compound of those two, as well as one of these two. So, if we are trying to charge balance, what do we need to do here, right? We're going to get Ag2CO3 is one product, right? Since carbon is 2 minus silver is 1 plus, we're going to need 2 silvers to balance that out. Yes, exactly. All right, and then yes, you've got KNO3 already. So notice that potassium and nitrate have the same charge, so we do not need any subscripts there. So we would predict our products to be silver carbonate and potassium nitrate. So notice the names also just swap. So we make silver carbonate. Oh, I forgot all my fun colors. Silver carbonate and potassium nitrate. So the ions are swapping, and so as a result, your names are also going to swap. So if all this charge balancing stuff, maybe you don't want to think about it in terms of, symbols with their charges. If you can translate the names, you can do it that way too. So let's see another example of this. I'll leave it on this screen for another couple of seconds. So yeah, exactly. So you should get a silver carbonate, so Ag2CO3, and then potassium nitrate. Okay, so let's look at this one. I'm going to give it to you in words. So lead 2 acetate plus potassium iodide. The products we're going to get out, sorry, since I don't have the room, I'm just going to put the arrow here. We would just swap the names. So this would be another way you could do it. If you really like the names, which probably none of you do, but if you like the names, you could just switch them. You could get lead 2 iodide plus potassium acetate. So we just swap the ions. So iodide and acetate gets swapped. So notice we just swap our anions. You could swap the cations too, it doesn't matter. You just choose one. And so by doing that switch, we get lead 2 iodide plus potassium acetate. And then we just have to translate from the name into a formula. Let's use dark blue for this. Lead 2 plus, of course, is Pb2 plus. Iodide is I minus. Do your crisscross. You get Pbi2. Potassium is K plus. Acetate is here. They're both the same charge, so we can just glub them together. And that would be the products of our reaction. So you can do it either way. You can use the names of the compounds to figure out the products, or you could look at the ions in the compounds to figure out the products. So nothing is changing here. So just another way for you to figure out the products of this reaction. All right, is that okay? We'll do more, but I just want to make sure we're okay with this one as well. Which method do you think you like more? Do you like the naming one or the looking at the ions and just swapping those, or the formulas, rather? Just so I'll be consistent in which way I solve these with you guys. Personally, I prefer looking at the formulas, but that's just because I've done this for quite a while, so it's second nature to me. Formulas, I think, okay, yeah, we can do that. Okay, awesome, great. Okay, then we'll do formulas. So, but just for anyone who does prefer the name way, it'll work every time. Don't worry about that. Okay, let's do another one then. How about we have What are the products that are we going to get from this? Yeah, get out of here. I'm not going to color coordinate all of them. That would be really nice, but yeah, it's that'll take too long for me to do. So yeah, you do it on your homework. That's fine. So what do we think the products of this are going to be? And so just so we remember also, this 2 here is for balancing Banzing. That 2 there is only there to balance sulfur. So that 2 has no bearing on what your product would be. Your product might have a 2 there, it might not. It does not matter. You should always have properly charged balanced compounds. So that 2 does not have to go over to the other side. We're going to deal with that 2 when we talk about balancing the equations. But for right now, that 2 only exists to balance sulfur. And so once it's removed from sulfur, it may or may not come back. It just depends what your new anion is going to be. Okay, so if we look at these, hooray! That's wonderful, yes. If we look at these, Sherry's got exactly right. We're going to want to put, and so I'm going to do NABR first, that's just my preference. It does not matter. You put your answer as H2S first, that's perfect, don't worry. So we know now we're going to pair off sodium and bromide. And so by charge balancing that, we should get sodium bromide because they're the same ones. And then we know we need to pair off H plus and S2 minus. So we're going to get H2S by doing that. Excellent, excellent, excellent. Very nice. And again, do not worry. Swap the 2. That's okay. Put H2S first. Same thing. Okay, so notice we did not need to bring the 2 over from the sodium. That was there to balance sulfur. It's gone from the other side. Notice now we had to introduce a 2 for H because it needed to balance out the sulfur. So don't be, afraid of that. All right, let's do one more before I introduce our last one. The last one is a little bit easier than this, in my opinion. Okay, so let's look at, how about we do... No. Yes, that's all we're doing. Yeah. So notice if we crisscross here, we should get 1 and 1. If we crisscross here, we should get 2 and 1, which is exactly what we got for our compounds. Yes. So before we go on, let's just take a moment to look at these 3 kind of subscripts we have here. We have kind of 2 different kinds of subscripts. Just so we know, this is part of a polyatomic. And so we keep the 3. These ones are for charge balancing. Which means we ignore them. The crisscross is just for the purpose of charge balancing. So notice it's important that we can identify whether a subscript is part of a polyatomic ion or if it's just there for charge balancing purposes. And so we know that SO3 is a polyatomic ion, right? It's sulfite, SO3 2-. That 3 there is a important component of that polyatomic ion, so we cannot get rid of it. That 3 will carry over because that is part of our ion. The 2, though, that's for lithium, will not carry over. There's no such thing as Li2 2+. Like, that's mercury will do that, yes, but not lithium. And again, we do not have Cl3 3-. That is not a polyatomic ion. So those 2 subscripts there, we're not going to bring over to the other side. I mean, we may have to once we charge balance, but don't think of them as being part of charge balancing for the other side. Okay, so this one is made of those 2 ions. And second compound is made of those 2 ions. So what are we going to get out of this? LiCl, yeah, that's good. So we've taken these 2 and the others cross off. And I know, Brittany, the other one is more complicated, right? So we know we're going to be combining these 2. And so we can crisscross them. Perfect. Yes, we're going to get Al2 parentheses SO3 3. Yeah. So Sherry, double check your charge balancing there. Okay, very nice. And then just don't forget the 2 goes after the Al as well. So, yeah, perfect. Alrighty, that looks good. Awesome. So far so good, I think. I'm going to introduce our last one, which is a little bit easier than the other ones that we've seen. Or rather, easier than double displacement. It's a little bit harder than the other ones we've seen, but easier than the other one. And this is just going to be single displacement. Which is also known as substitution. You might also see this as single replacement. Again, same thing. Or substitution. And an example of this would be, let's see, what would be a good one? This would be an example of a single replacement reaction. So we have, how we can identify these, by the way, we have an element plus a compound. Compound is abbreviated CPD, at least for me. So that's what I mean by that. We produce a compound plus an element. Did we do this for the double displacement? Actually, I don't think we did. Let me scroll up real quick. Yeah, I didn't. Okay. Okay. Let me just write it down here. Sorry. So for double, we would do something like, I don't know. So we have compound plus compound turns into compound plus compound. So we have two ionic compounds coming to us. We're not going to worry about that. This is separate. Just unboxing it and doing it in purple. We are not going to have to predict it for us. For us, assume it will always work, okay? No, we're not going to have that. You'll have that in probably Gen Chem 2, where you're going to be looking at what's called a reactivity series, or rather an activity series, which is going to tell you whether or not it'll take place. For us in this class, it's always going to work. So we don't have to worry about that. Okay, so for a single displacement, you're going to see an element in a compound becoming a different compound with a different element. For double displacement, you see two compounds turning into two compounds. So, and for double displacement, it's always ionic compounds as well. Okay, so what do we see that's happening here in this reaction? We see that calcium is basically going in to the FeCl2, kicking out the iron, and putting itself in there instead. So let's take a look at another one. What do we think is going to happen here? So, I mean, we know we're gonna have to kick one of these things out of the ionic compound. We basically have two options. We have option one would be we kick out the chlorine and make this. Option two, we kick out the sodium and we get potassium chloride. Which one do... Okay, you guys have already done it, but yeah, obviously you should get the second one, right? Because you'd want to look at your element that's by itself. That's a metal, right? Metals don't form ionic compounds with other metals. Not going to happen. So we're going to actually kick out the metal, therefore. So basically you're just going to swap the metals. You're going to leave your anion alone, and that's the end here. So this is going to be our preferred one. We're going to use a metal to kick out a metal. If, however, we had, instead of potassium coming in, if we had fluorine coming in, what's going to happen here is, notice we have a non-metal now. That is going to kick out the non-metal. So if I kind of do our possible products again, we can get this FCl plus Na, or we can get NaF plus Cl2. And again, we're going to get that second one is our preferred one, right? So a non-metal will kick out a non-metal, a metal will kick out a metal. So that's really all it comes down to. So let me just write that down, and then we'll end for the day. Or, yeah, that's just fine. And then non-metals replace non-metals. I'll fix that. So that's all we need to know for this reaction. So we're going to continue with this on Monday. And then we're going to start talking about observational types of reactions as well. And then we'll talk about balancing and states of matter and all sorts of fun goodness to decorate our reactions. Okay? Exciting. With that, tomorrow it looked like a lot of you guys had exam questions, so we'll go over those tomorrow. So go ahead and take your screenshots, drop them in Discord. We'll have those there. I guess I should make the announcement anyway. I did send out an email. If any of you are considering dropping, Friday is the drop deadline. So if you have to make that choice, make sure you do it by Friday, because afterwards you're stuck with me. So and then I don't want to have to fail anyone. So yeah, it's not an easy discussion, of course, but you can reach out to me if you have any concerns. I did put some things to think about in that email regarding homework and exams and all that stuff. So just take a look at it, and if you have questions, feel free to ping me on Discord or something, or if you like email, that's fine. Alrighty. Yes. Yep. See you, Brittany. You do not need the activity series. I can give it to you if you want, but for these ones, I prefer just not to do it because it's easier for me to think of problems off the top of my head since I do not have the activity series memorized. Yes, you will have post-exam homework. Did I not put that up? Oh, I think I meant to do that yesterday. But yeah, you'll have that. So that's going to be your homework this week, is just the post-exam stuff. I'll put that up right now, so you guys will have that. It's the same as all the other ones. So, okay. Kenji, if you want to continue this, hop into Discord. I'm just gonna stop streaming for a sec. So, yeah. Okay. See you guys tomorrow.